Good morning, class. Welcome to your last week of distance learning for the SPHS 2019-2020 academic school year. I'm sure this is not how you wanted to spend your last weeks of school, but here we are. This week in stats, you are going to learn how to use something called tree diagrams to solve some probability problems. Last week, you had a problem in the check your understanding that I think a lot of you didn't know how to do. I put it on there just to see if you could come up with something clever, but this week you're going to learn how to solve those using tree diagrams. So let me share my screen and show you what you're going to be up to. So we're going to be working on the 15.4 section of the website. So if you have a look under part 4, you're going to go to 15.4 and you're going to be playing. Last week you played the most boring dice game ever. This week you're going to be playing the most boring card game ever. If you don't have a deck of cards, I'll show you how to modify that in a bit, but all you need is 5 cards total, so you don't even need a full deck. The very first thing that you could play around with if you have some spare time is this game here. There's a game called the Monty Hall Problem. This was a game maybe back in like the 70s that people would play, kind of like Wheel of Fortune or whatever that game with the Plinko stuff is. But what you would be asked to do was pick a door, and then the host would reveal some information and then ask you if you would want to switch your door to try and win a fancy car. Behind the other 2 doors were goats. When I played this in past classes, students have said, well, maybe I actually want to win the goat, and kind of have turned this on their head. But the idea is I would pick a door. Let's say I want to pick door number 2. The host would reveal that, hey, look at that. There's a goat behind door number 1. Good thing you didn't pick that. Do you want to stay with door number 2, or do you want to switch to door number 3? And so let's say, okay, I'm going to switch to door number 3. Oh, look at that. Gotta go. Didn't totally win. So you can play this again and figure out if it's worth it to switch like I just did there, or stay with your door. And this is something that you can actually solve with tree diagrams. It's a bit more complicated than what we're going to get into today, but if you're feeling up to the challenge, you can have a look at that. All right, so I'm going to do a little video tutorial about how to use tree diagrams in general, and then you are going to work on the 15.4 most boring card game ever to turn in. So let me pull up my iPad. So this was one of the questions that you had on your homework. The probability of rolling a 4 and then a 6 with a 6-sided die. A lot of people said, well, okay, there are 2 choices, a 4 or 6, and there's 6 options. So I'm going to say it's a 2 out of 6 chance. This is actually not the correct answer, right? The chances would be the same as a 1 out of 3, which would be more likely than happening if you were to look at just say rolling a 4. So rolling a 4 and then a 6 is a very specific thing that you want to happen. And because of that, the probability is actually going to be way less than just rolling a 4 or just rolling a 6. So with this, we've got 2 events that are happening. So rolling a 4 is one event, and then rolling a 6 is another event. Sequentially, I'm going to say that the 4 is going to happen first, 6 is going to happen second. And so if I was looking at all of the possibilities for just rolling any 6-sided die, let's say that this is my starting point right here. I'm going to say, well, one option is I could roll a 1, I could roll a 2, I could roll a 3. Those are going to have to get moved because we're going to have a lot of choices here. Let's do it like that. I could roll a 4, I could roll a 5, or I could roll a 6. And if I was just looking at rolling a 4, there's one chance out of those 6 that I would get it. So rolling a 4, you already know that it's 1 out of 6. Let's make this a fancy color because that's the one we're interested in. All right, so if I roll a 1 and then I roll the dice again, there are still 6 more possibilities that I could roll. So I could still roll a 1, a 2, a 3, a 4, a 5, or a 6. 1, 2, 3, 4, 5, or a 6. And this is going to be true whether or not I roll a 1, I roll a 2, I roll a 3, I roll a 4, oops, 5, or a 6. And the only one that we are interested in, the only one that is the outcome that we want is I roll a 4 and then I roll a 6. So let's highlight this guy right here. So if we look, there are a total of 6 things per each 1, 2, 3, 4, 5, 6 original 6 things that I could have rolled. So if I counted up all of the branches, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way to 36, that's the new denominator of my fraction. So of the 36 choices that I've got, I'm only successful once. You might think, wow, it's kind of a pain to make this tree diagram for this scenario. You're correct. Sometimes you might have to make a tree diagram because that might be the only way of solving something. But for this, the other way I could have solved it is I could have said, well, for that first roll, I had a 1 out of 6 chance of getting what I wanted. For that second roll, I also had a 1 out of 6 chance of getting what I wanted. And for this, what we're going to do is we're going to multiply tops together, multiply the bottoms together, and that's how I end up with my probability. So a tree diagram is a really nice way of setting this whole thing up to see what numbers you're working with. So this is a worksheet. I have it linked on the website if you want to follow along or have some notes to look at. It's linked on there. The completed notes will also be up on the website, but this kind of describes how you want to create your tree diagrams. This one has the probabilities listed on it, which is something that I want you to do. I didn't do it on the last one because it would have gotten way too cluttered, but basically what we're doing is if we look at this first one, this is the tree diagram for flipping one coin. So you always start with kind of like this dot to say, here's my starting point. You make branches that show all of the possible outcomes. So heads or tails would be the only possible outcomes. And then the probability of each one goes along the branch. So the probability of flipping a coin and it being heads is 0.5. Same for tails. Probability of flipping a tails and being flipping a coin being tails is 0.5. So that's something pretty simple tree diagram with just one event. Down below, or nope, over to the right, we've got a probability with 2 things. So I'm going to flip a coin once, flip a coin twice. This is kind of like the dice example that I just showed you. So with this, we're going to have the same setup as before, where we're going to have heads and tails are my first outcomes with the probabilities 0.5 and 0.5 listed. And then from there, I'm going to say, well, if I flip a head, there are 2 possibilities for the next coin. So it could still be heads or it could be tails again. The probability of it being heads is 0.5, probability of being tails is 0.5. And then on the other branch, if I flip a tail and then I flip the coin again, my 2 probabilities are still 0.5, 0.5 for heads and tails. The final step that a lot of people tend to forget to do is to get the probabilities of each of the branches. So in order to get the probability of flipping 2 coins and getting heads twice, I would take the probabilities along the branches and multiply them together to get the final probability here. This one is kind of boring because all of the probabilities listed are 0.5, but you would do the same thing, 0.5 times this 0.5 to get this probability here, this 0.5 times this 0.5 to get this probability here, this 0.5 times this 0.5 to get this probability here. And then the one thing that you can do to check your work is that you should be able to add all of these up, and they should always add up to 1 or 100%. Whenever you're multiplying these, please do not write them in terms of a percent. Please write them in terms of decimals. All right, so let's do an example to show you how you might try and solve this thing. So we've got a battery factory, very exciting stuff. They produce 2 types of batteries, regular and rechargeable. So we've got one event, probably one event here. Quality inspection tests show that 2% of the regular batteries come off the manufacturing line with a defect, while only 1% of the rechargeable batteries have a defect. Rechargeable batteries make up 25% of the company's production. Calculate the probabilities for each of the 4 branches on the tree. So the very first thing I have to do is figure out which one of these events happened first. So are the batteries defective or not first, or are they created as a regular or a rechargeable first? Hopefully that is obvious to you, but this one is my first event, and then this is going to be my second event. So I'm going to start here by saying, all right, I've got 2 options for how batteries are produced. They're either going to be regular or rechargeable. And for the percent, rechargeable batteries make up 25% of the company's production. So down here, there's a 25% chance that a battery would be rechargeable, and I can infer that 75% of the batteries would be regular. Gotta grab a calculator, hold on. All right. For the second event, when the batteries are produced, there's a possibility that they could have a defect. On the other hand, there's a possibility that there is no defect. Same thing for the rechargeable. Either they're going to have a defect or not. And now we have to fill in the probabilities for those things. So quality inspection tests show that 2% of the regular batteries have a defect. So 2% would be 0.02. So I can assume that 98% have no defect. 1% of the rechargeable batteries have a defect. So 0.01, and then no defect 0.09. So now what I have to do is calculate the probability for each one of these branches. So the probability that the battery is regular and has a defect, the probability that it's regular and has no defect, rechargeable defect, rechargeable no defect. And what I'm going to do to get this very first one, I'm going to say 0.75 times 0.02 and get 0.015. Right, for the next one, regular and no defect, 0.75 again, 0.98, 0.735. For rechargeable defect, I get that. And then the last branch, 0.25. Oops. That should say 0.99. Let's say I did make that mistake. Let's say I left this as 0.09. What I would have gotten for my answer would have been 0.25 times 0.09, 0.0225. I would have been able to figure out pretty quickly that I had a mistake in my work when I added up all of my probabilities. So if I were to add up these numbers here, they certainly wouldn't add up to 1. But if I add up the correct numbers, so 0.015 plus 0.735 plus 0.0025 plus 0.2475, sure enough, it equals 1.0. So I know all of my probabilities are calculated correctly. That is good. Now I can go and figure out what's the probability that a battery is defective. So it doesn't ask me if the battery is regular or rechargeable or not. I just want to know if they have a defect. So what I'm going to do here is I'm going to have a look at all of the branches that show me a battery ends up defective. So I see that this very first branch would end up in a battery that's defective. Second one, no defect, don't care about that. The third one has a defect, and then the last one does not. So what I'm going to do is say the probability that a battery is defective is 0.015 plus 0.0025 and get 0.0175. So I could say 1.75% of the batteries will be defective. If you want to try out some other problems, there are some more on the assignment here. This one, the finals one, is a very tricky one. It involves a lot of different branches. It's all about getting accepted to college. I don't know if the data is made up or not. Sorry, that one's not there. University admissions. This one's a little bit tricky, so if you want to play around with that one, you can. For what you're going to do, you're going to play the most boring card game ever. And for this, you're going to need 2 red cards and 3 black cards. If you don't have that, but instead you have dice, those will work instead. If you don't have dice, you can, I don't know, skip playing the game, although you'll be not able to be bored out of your mind, I guess. If you want to use dice instead of 2 red cards and 3 black cards, I would recommend saying the 2 red cards would be represented by rolling a 1 or rolling a 2. The 3 black cards would be represented by rolling a 3, a 4, or a 5. If you roll a 6, just ignore it and re-roll. But what you're going to do is, if you want to play this with someone, you can, or you can play it by yourself. Doesn't matter. But the player is going to choose. You're going to have your 5 cards, shuffle them around, and then randomly select one of the cards. So all the cards face down. Don't look at them. Pick a card. And then pick a second card. If you get a pair of red cards, you win. If you get a pair of black cards, you win. If you get a red or and a black, you don't win. For that, you're going to record your results on the table here, calculate the probabilities that you've won, so something out of 10. And then you're going to use this tree diagram to calculate the actual theoretical probability. So the probability underlying this whole thing, not just based on your sample. If you're working on a computer, you can double click on this and you can fill in the probabilities here and then fill in the probabilities for each of the branches along the lines. So they're all little text boxes. Um, Other than that, for the big ideas, I'll have that filled out in the filled out version of the notes. But the general multiplication rule is that rule that we talked about at the very beginning. So multiplying the probability of one event times the probability of another event to find the probability of those two events occurring simultaneously or one right after each other. And then tree diagrams, hopefully you won't need a lot of write-up about that. But using tree diagrams to model probabilities, always something very useful. For the work that I'm going to look at, this is the check your understanding part. Again, you can double click on this, fill in the probabilities if you're working on your computer. But you're going to model this scenario listed above in the tree diagram below, and then calculate some probabilities for those. So there's one about some dice, there's one about Jack waking up for school, there's one about soccer players, and then there's a challenge problem here that if you want to give that a shot, it's referring to the first problem above. So that's it for this lesson. So as of now, you've learned how to use Venn diagrams, two-way tables, and hopefully now tree diagrams to model some probabilities. And check Neo for some information about what we're doing for CAP. And otherwise, hope you enjoy this 40-degree day.